All right, welcome to our 16th lecture in this series on algebraic topology. I'm Norman Wahlberger at the University of New South Wales. We're going to carry on with what we were talking about last time. We were talking about the rational curvature of the polytope. And today we want to finish that off and extend it so that we can connect curvature with the Euler number. So let me remind you of the setup. First of all, we are talking about rational curvature, which is 1 over 2 pi times the usual notion of curvature. And so for a polygon on the surface of the sphere, a spherical n-gon, say, the total solid turn angle that we're talking about, calling it omega, is, by a theorem of Harriot, the sum of the individual internal turn angles minus n over 2 plus 1. And in particular case, when n is 3, an important special case of a triangle, then it's the sum of the 3 internal tangles minus a half. And that's the situation that we're using over here to define the curvature of the polytope. So the definition of the curvature of a polytope P at the vertex A, this is, by definition, the solid tangle of the opposite cone. The solid tangle, omega, of the opposite cone. So in the case where we have A has degree 3, with, well, I can just here, so with turn angles tau 1, tau 2, and tau 3 at the vertex, tau 1, tau 2, and tau 3. In this case, the curvature is, well, first of all, it's mu1 plus mu2 plus mu3 minus a half. And then each one of the mu i's was a half minus the corresponding tau I. Because the angle between two edges here is complementary to the angle between the perpendicular faces. So they add up to 1/2. So we had 1/2 minus tau 1 for mu1, plus 1/2 minus tau 2 for mu2, and 1/2 minus tau 3 for mu3. And when we subtracted 1/2, we got this fundamental formula, 1 minus tau 1 plus tau 2 plus tau 3. And now what I want to do is look at the same thing with the general situation where the A has degree n. So there are n edges coming in at the vertex A. So there's A. These various faces that meet at A have tangles of tau 1, tau 2, tau 3, and so on, all the way up to the one at the back, tau n. All right, so now what's going to happen is that those n faces will have n perpendicular directions. So each face here is going to have a perpendicular direction. Okay. There are going to be also n edges coming out perpendicular to the n faces that meet here. And that's going to form our opposite cone. Okay. Just in exactly the same way. And then we're going to have on the surface of a sphere centered at A, there's our vertex A, well, that opposite cone will give us some polytope on the surface of the sphere. And if we look at any one vertex of that polytope, say that one there, that vertex is the meeting of two faces. And the faces of this opposite cone are perpendicular to the edges here. It's a duality, so that the faces here are perpendicular to the edges here, and the faces here are perpendicular to the edges here. So a particular vertex in this n-gon up here has two faces, one of which is perpendicular to one of these edges, and the other one which is perpendicular to the other edge. So if I kind of do a cross-section of that situation, those are the two edges in question. And then the two perpendicular faces are kind of coming out something like this. So exactly the same relation will happen, that if that is a turn of tau I, then this turn between these two faces will be mu I, which will be 1/2 minus tau I. So in other words, this spherical polygon formed by the opposite cone will have turns mu1, mu2, and so on. So the tangles of the opposite cone at the vertex A has internal tangles mu1, which is 1/2 minus tau 1, and then mu2, which is 1/2 minus tau 2, and so on up to mu n, which is 1/2 minus tau n.
Can we describe it as a cone?
This is a cone. This is a cone coming up, and that cone intersects the sphere, centered it here, in a spherical n-gon. So it's exactly a generalization of what we were doing over here, for example. In the case of just a vert degree 3, that was the original polytope. There was the dual or opposite cone. And when we intersect with the sphere, we look at this cone intersected with a sphere centered here. It picks out a spherical triangle on that surface of the sphere. And the angles or tangles of that spherical triangle are just the angles or tangles between the faces of this cone. All right, so we can now say what is the curvature at A. So the curvature at A is curvature of the polytope P at A is, well, by definition, it's the solid tangle of this spherical n-gon. So it's equal to mu1 plus mu2 plus mu n, using the formula that's right over there, minus n over 2 plus 1. That's what we were calling omega. And now observe what happens when we replace the mu's with the 1/2 minus the taus. So we get 1/2 minus tau 1 plus all the way up to 1/2 minus tau n minus minus n over 2 plus 1. And there are exactly as many halves here. There are n halves, which exactly cancels with this n over 2. And we're left with 1 minus tau 1 plus tau 2 plus tau n. It's the same kind of formula as we got for the triangle case. All right, so we've just state this in a theorem that if a polytope P has vertex A with tangles of the faces at A being tau 1, tau 2, up to tau n, then the curvature of P at A equals 1 minus tau 1 plus tau 2 plus tau n. All right, so it's time to do some examples. First one will be tetrahedron. And we'll make it a regular tetrahedron so that it's easier to compute. Although it doesn't have to be a regular tetrahedron for the total curvature. But to make the individual curvatures easy to calculate, let's make a regular tetrahedron. So there it is right there. So if we take a vertex, what are the tangles of the faces that meet there? Well, each equilateral triangle has a tangle of 1/6 of the way all the way around. That's 1/6. Same as 60 degrees. It's a tangle of 1/6. So the curvature at the vertex A is 1 minus 1/6 plus 1/6 plus 1/6, because there are 3 faces meeting at the vertex. 3 tangles of 1/6 for a total of 1/2. And the total curvature of the entire polygon, well, there are 4 vertices. So we have 4 times 1/2, which is 2. Example number 2, our cube. So now if we pick a vertex, then each face at that vertex is a right angle, so a quarter turn. So the curvature, say at A, equals 1 minus, well, there are 3 of them, so 1/4 plus 1/4 plus 1/4. That's a total of 1/4. And the total curvature is, well, there are 8 vertices, so 8 times 1/4 is 2. Example 3, the octahedron. to the vertex A. Now the curvature at A is 1 minus turn of 1/6, still because it's an equilateral triangle, but now there are 1, 2, 3, 4 of them. So we have to subtract 1/6 plus 1/6 plus 1/6 plus 1/6. That's 2/3, so 1 minus that is 1/3. And the total curvature is 6 times 1/3, which is 2. Okay, example 4, the icosahedron. Well, at a vertex, we have 1, 2, 3, 4, 5. We have 5 equilateral triangles coming together. Won't draw the rest of it. But the curvature at A, it's 1 minus the sum of the turns that meet here. And so it's 1 minus 5 times still 1/6. So it's an equilateral triangle, which is 1/6. And how many vertices are there altogether? There are 12. So the total curvature is 12 times 1/6 equals 2. And finally, our dodecahedron. Well, for the dodecahedron, we had pentagons coming together. 3 pentagons. And what is the internal tangle of a pentagon? Well, I think I computed that last time. I think we found that it was 3/10. And so the curvature at A will be 1 minus 3 times 3/10, which is 1/10. And the total curvature equals, well, there are 20 vertices, so it's 20 times 1/10, which is still 2. And now also this makes it very clear that the dodecahedron is the roundest. Because it has the smallest curvature. At every vertex it has a curvature of 1/10. The icosahedron a little bit more, 1/6, 1/3, 1/4, 1/2. So actually it's going up, right? In this order. We can quantify how much curvature there is at a particular point. All right, so problem, is it 18? Thank you. Problem 18, compute directly the curvature at a vertex for a truncated octahedron and B at truncated icosahedron. And find the total curvatures. Now I remind you that a truncated octahedron is, you get an octahedron and you chop off the top. So you make a little square face there. So there are some square faces and hexagonal faces left over. If you do it in a regular way, in the right way, then it becomes an Archimedean solid, so it's regular. And the icosahedron, if you chop off a little area near a vertex, you get a little pentagonal face. And you get pentagonal faces and hexagonal faces. Okay, so now let's have a look at why are we getting 2 in all these cases, and do we get 2 no matter what we start with? So suppose we have a number of polygonal faces meeting 2 at a time along an edge to form a polyhedron. But let's suppose that it's not at all necessarily regular. So we've got some very generic object. Forming some object in space, let's say. And we want to find out what is the total curvature. Well, first of all, it's the sum over all the vertices of the vertices, let's call them A, of the curvature at A. That's what we mean by the total curvature, the sum of all the curvatures at all the vertices. Okay, so let's suppose that the turn angles at our vertex AI are tau 1, tau 2, up to say tau k. All right. So our formula for the curvature at AI is 1 minus sum of tau 1 plus tau 2 all the way up to tau k. That's our formula for the curvature at AI in terms of the tangles that meet at, or the faces that meet at the vertex AI. Okay, so we're going to replace this sum. So it's a sum of all the vertices. We'll just write sum over the vertices. And then we have to sum 1 minus tau 1 plus tau k. Yeah, the k's are going to be different, so maybe I should put ki here, make it clear that it depends on the vertices. So maybe I'll write vertices ai. Okay, what happens when we sum this whole thing up? So there's one such sum for every vertex. So this one term is easy to sum. It's going to be 1 for each vertex. So that's going to give us the total number of vertices for sure. Okay. Now what about this? Well, what is this? This is just the sum of all the turn angles that meet here. And that has to be done at every vertex. So we have to sum up all these turns, and then all these turns, and all these turns. So basically, as we vary over the whole thing, the second thing is the sum over all the face turns in the whole polyhedron. We're just summing every single one of them. All of them. Because each one of them appears at exactly one vertex. So we can write, okay, it's V minus the sum over all the faces of the sum of the face tangles, or sum of tangles, let's say. Now, each one of these pieces is actually a planar piece. Okay, so it's a planar piece. And what do we know about a planar polygon? So for a planar polygon, tau 1, tau 2 up to, say, tau k, we know that tau 1 plus up to tau k, what is that actually equal to? So this is a planar situation, like a triangle. So for a triangle, it was a half. For a square, it was 1. For a pentagon, it was 3 halves. So it's k over 2. K over 2 minus 1. Okay. So we can rewrite this sum over all faces of the sum of the tangles, because we know what the sum of the tangles is for any one individual face. It's the number of faces divided by 2 minus 1. So this is V minus the sum over all the faces of, let's say Ki over 2 minus 1. Okay, what is that? So what is this? This is the sum of over all the faces of the number of edges in that face. Okay, so we're counting the number of edges in this face and dividing it by 2. And then we're counting the number of edges in the next face and dividing it by 2 and adding them all up. Edges. So what are we getting here in this Ki over 2 is the sum of that is the sum of all the edges. Exactly the sum of all the edges, because we've counted all the edges twice. Every edge appears in 2 faces. It gets counted twice. And we've divided by 2 very conveniently. So we're getting V minus the sum of the faces of Ki over 2 is just the number of edges. And then there's a plus 1 sum over faces, so that's plus F. So whether it's convex or not, that's the Euler number. All right, so this is kind of a very nice little situation. So let me just say a few things about okay. Let's say you have this is a deltahedron made out of triangles. And so let's say at this corner here, there are 1, 2, 3, 4 triangles meeting. Each one has a turn of a sixth. So 4 times 1/6 is 2/3, so that the curvature here is 1 minus 2/3 of 1/3. Okay. Over here, we have 6 of them meeting. 6 times 1/6 is 1, and 1 minus 1 is 0. That means the curvature here is 0. It's bent a little bit. You can see it's bent. It's actually, this is a straight line here, but it's bent. But nevertheless, the curvature here is 0. But what's a little bit more interesting is this vertex right here. I've cooked up 7 triangles that meet at that vertex. At this vertex right here. You can count them. 1, 2, 3, 4, 5, 6, 7. So what's the curvature at this vertex? Well, it's 1 minus 7 times 1/6. That'll be minus 1/6. That means there's negative curvature at this point here. This is the surface is negatively curved at this point here, and this curvature is picking that up. So this is an indication that somehow, okay, well, negative curvature is usually associated with hyperbolic geometry. That hyperbolic geometry has something to do with surfaces sometimes, and that turns out to be very much the case in a very interesting way. But if you calculated the total curvature, including that minus 1/6 for a delta hadron like this, you'd still get the Euler number, 2. This is a flexible notion. It can be negative. It can even be bigger than, well, it can be quite arbitrary if we allow rather random things to happen. So to give you a little bit of practice thinking about that, here's problem number 19. So,
that gives you a sense by the solid isn't convex.
It's not convex. That's right. It's not convex. Yep. It's sort of associated with having going in this direction and one direction going in like a saddle shape, in differential geometry. So compute directly the curvatures of the following solid. So take a cube, and now we're going to drill a hole through it, a square hole. Well, dot. So we're drilling a square hole through it. And to get kind of sides which are sort of decent polygons, we'll split this front face up into 4 quadrilaterals. And we'll split the back face up exactly in the same way into 4 quadrilaterals. Okay, so this is made out of, I think they're all rectangular pieces or quadrilateral pieces. One side for the top, one on the bottom, on top, and then there's these quadrilateral pieces. And inside, there's also pieces. So there are the usual 8 outside vertices, but there are also these 8 inside or hole vertices.
Is the cube in the middle smaller?
Yeah, this cube, we bored a hole through the cube. So it'd be like taking this cube here and just drilling a square hole right through the middle. Cutting a square there and drilling it right through. And thinking of it as a solid object that we've just drilled like an apple core out of it. So you could touch it. And you could count. You could compute the curvatures at each of the vertices, which I want you to do, and then to add them all up to find the total curvature.
You can achieve all angles in a nice, like 45 degrees.
Yes, you can make them nice so that they're nice angles that you compute with. This is all nice and regular. Compute directly the curvatures of this cube with square hole. And the total curvature.
The face with a hole in it is not planar, right?
Say again?
The face with a hole in,
Yes.
it's not. Is it planar?
Yeah, everything's flat.
So those 4 edges that come out.
These ones?
Yeah.
This is the front part. Here what you're seeing is the front part of the cube. The front part of the cube looks exactly like this.
And it's flat.
And it's flat, completely flat.
Wouldn't make any difference, though, would it?
It wouldn't make any difference in terms of the total curvature, but in terms of computing it, it might make a difference. Okay, so next time we are going to move towards the main theorem in the subject, is the classification of surfaces. Okay? So we're going to look at this problem from a number of different points of view. A classical point of view, look at Conway's zip proof, and we're going to have a lot more things to compute. So I'll see you then.